All right, two important things before I jump in. The first is, can I see a show of hands, who here has already used Hypothesis? All right, hands down. Who here has not used Hypothesis? Thank you, hands down. And who here just doesn't put their hands up when I ask questions? Several people, excellent. Thank you for your participation. And the second is that this talk is going to have a couple of live demos. And I want this to feel a little interactive. So every time I say the words live demo, I want you to say what could possibly go wrong. Are we ready? This talk will have several live demos. What could possibly go wrong? Thank you. All right, and now let's jump in. So, Hypothesis is a library for writing better unit tests. And standard unit tests might look something like this. You write tests that say, given some particular input, I'm going to run my code, and then I'll check that I got a particular output. Or maybe you just check that it didn't crash. And you can kind of improve on this by using Pytest to have like a table of input and expected output data. And so this makes it much easier to add additional cases that test the same thing. And you can do even better sometimes where you might not need to know what the exact output will be if you can just have a trusted implementation that you compare to. And so this just says, like, given a couple of lists, if I sort them, I get the same result as my trusted implementation. And you might be thinking, when does this ever come up in practice? Who here has ever written multi-threaded code? You can just run that code with one thread and check that you get the same result. But if you don't have a trusted implementation, you can still check some things. So if we just imagine that we have no idea how to sort things, we could still say that, like, well, we can check that the output is in increasing order, right? So that would be a good start. But that could still have a bug, so we also need to check that we have the same elements afterwards. We don't want our sorting function to return the empty list, even though the empty list is sorted. But also, if we have duplicated elements, then we need something a little more complicated, which we get through. So where does Hypothesis come into this? Well, this style of test is already a property-based test, which is the kind of thing Hypothesis does. And what Hypothesis saves you from is the ellipses, where you have to work out what the inputs are. Because we often have this mythology around testing. We're like, okay, so first I'm going to write some code, and maybe I didn't quite understand the domain, or maybe I forgot something, or I just had a typo. And then I'm going to tab over to a different file where the file name starts with the word test, and I will spontaneously remember everything I previously forgot. But if that doesn't work, then Hypothesis is pretty useful. Hypothesis generates the inputs to your test function for you. So this is kind of the core proposition. Instead of having to think of all of the different lists of numbers or lists of strings you could have, Hypothesis will generate those edge cases for you. And in fact, it will tell you that this test fails if you put in the list containing a floating point nan, because not a number is not equal to or less than or greater than anything else. It just returns false from these comparisons. And so this just taught us something about our domain by having the computer think of the edge cases for you. So that's classic Hypothesis. But what I'm going to talk about today mostly is a couple of live demos of some new features in Hypothesis that I really enjoy. The first of those features is the ghostwriter, a technique where we get computers to write code so that you don't have to. But I wrote this well before I joined Anthropic, and there are absolutely no language models under the hood. This is old-fashioned AI, where I wrote a bunch of regular expressions and lookup tables and if statements and string templates, and it works pretty well considering. Then I'll come back, I'll talk about some alternative backends which do more effective searches, and then I'll talk about observability, because we all love knowing what the heck just happened. So, first up, a live demo of what I call the ghostwriter. I originally developed the ghostwriter at the start of 2020, after I'd been to PyCon 2019, and lots of people said things to me which sounded like, Hypothesis seems really cool, but I don't use it because I'm not sure how to apply it to my code. And I thought to myself, every software engineer dreams of finding a social problem with a technical solution. Maybe this is it. Maybe if I try hard and believe in myself and write some Python, I can help people use my Python library. So we're going to see how well that works. We're going to tell Hypothesis to write a test for what module should we test? How about gzip compression? So this will think for a moment. It works entirely offline because no language model, and we get an instant test. And so let me zoom in a little further. What does this test do? It says, given a compression level and the data to compress and the modification time, we should compress that thing, then decompress it, and check that we got the thing back. What do we think happens if we run this? It does indeed fail, and it fails because we've just said that we're not generating anything for the data. So we actually want binary strings there. And if we run this, the test should pass. I forgot to save the file. So if we fix that, it should work. I love live demos. Thank you, thank you. All right, so we could also try something a little more ambitious. We could try writing a test for, let's say, JSON. And if we write our test for JSON serialization, who here's used JSON? Jason's a great guy. It turns out there are a lot of arguments to JSON serialization in Python. But the one that we really have to fill in for ourselves is the object. It's like, what's the definition of JSON objects? Anyone? You can have none, or you can have a Boolean, or you can have integers, or you can have floats, or you can have a string. Yep. And then you can also have lists of JSON, or you can have dictionaries where the keys are strings, and the values are JSON. All right, if I save the file this time, then what we should see is this test going to pass or fail? Anyone? I see a shrug. Any other takers? Anyone? Anyone? No? Well, the fun of live demos is that sometimes my laptop running on battery power takes a little time to run things. What we will see sooner or later is that if you have a floating point nan, then JSON serialization does not give you an equal object, because nan is not equal to itself. So we're going to go a little further. We're going to add an assume, which is a hypothesis function that's kind of like an assertion, but it just says, if this doesn't hold, just throw out that test case and try something else. So we're going to assume that the object is equal to itself, and then we're going to allow nan, so this will be just true, because the JSON spec also doesn't, strictly speaking, allow infinity. So if this test had finished running because my laptop was not power throttled, we would have seen some demonstrations of that. You do get more output, but not from while it's running. So we get an assertion error here. which tells us a couple of things. The problem is if we have a dictionary where the value is nan, this dictionary compares equal to itself. It turns out that Python's built-in collections have this nice performance optimization where they just do pointer equality checks first because that's fast. And nan is kind of like not really in the object model of how equality is meant to work. So we would have to specify if we wanted this test to pass, allow nan equals false. Now the test will pass. Okay, so far so good. But the example we get is actually a minimal failure example, and this is pretty important. And hypothesis will even go further. It will tell you sometimes that some arguments can take on any other value that we tried and still give you the same failure. So this makes it somewhat easier to work out what is going on when your tests fail. And as far as I know, hypothesis is the only such tool that does this. So, the ghostwriter is pretty cool, but it's not the only feature I wanted to talk about. The second is fuzzing. So hypothesis by default is sort of organized around a unit testing-like workflow, where you stand on stage and you run your code and you want it to give results really quickly. Or maybe you're at your desk and you're preparing a pull request and you want it to give you results quickly. But because this is a search process, it would also be reasonable just to leave it running overnight and come back in the morning and see if it had found any bugs for you. And in that different setting, it's actually worth using smarter techniques that have a bit more overhead, but scale better over time. And so this graph shows 3 different techniques based on coverage-guided fuzzing. The green line is actually just the default performance of the random backend. And so you can see that over a 10-minute run, the orange line, which is our sort of old, bad fuzzing approach, just like hacking stuff together, it's still scaling up, so it does overtake if you leave it running for long enough. And the blue line is our more recent fuzzing experiments, where we're using an alternative backend which is much more tightly integrated with the way hypothesis works. And you can see that it first overtakes after, I think, about 4 seconds. And so if you're running for your tests for as long as 4 seconds each, this is already better, and it will tend to continue overtaking over time. And if I run the fuzzer, we also get a really nice web interface which tells us what's going on. So this will take a moment because the thing is optimized around running for 6 hours or so. But once we start getting data show up, it will tell us what test function or functions we're running. And it will also give us a good estimate of how long has it been since we last found some new coverage, and what's the statistical estimate of how long we will have to run for before we find a bug. Live demos, eh? Thank you, audience. It's so much more fun to play this game together. So what we would see, if the thing had loaded more quickly, is something like this. You can see a graph of coverage over time for all of the different tests, and you can also inspect what different test cases got different coverage. If something fails, you get a little explosion emoji, because why not? And importantly, hypothesis has this concept of a database. So if we ever find a failing example, we'll store that in our database and replay it from then on. You can run hypothesis in a completely deterministic mode, but I actually prefer the non-deterministic mode, where you're not guaranteed to find an example at any particular time, although it's likely, but once it's found, you don't have to wonder whether your fix has actually fixed the bug or just not found the bug again, because it will replay that same input again and again until the test passes. And that integrates. The fuzzer uses the same database. So you can share a local directory on your developer machine. You can put the key value store in a shared Redis server for your whole team and your CI system. And you can run this mixture of fast local searches for bugs to check that you haven't introduced one, with more expensive, longer running searches with a shared database. And I find that's a really nice workflow. There's also, let's just see if the fuzzer has found anything yet. No. what you would see is a line on this graph, if only it had showed up yet. We're just going to leave that running, actually. So let's pop open a new terminal. I didn't even say live demo. There we go. So the last tricky thing is sometimes you have bugs which only trigger if there is a single exact input that makes them fail. And maybe that input is not a number, but Hypothesis knows about not a number. It knows about plus and minus 1, about 0, about 2 to the power of 64 minus 1, and other fun edge cases that might cause things to go sideways. But if you have just a random 1 in a billion value, like 1, 2, 3, 3, 5, 6, 7, 8, 9, like what are the odds of this? No one would even put this in as a special case because I typoed it earlier today. And so it's just really not clear how you could ever find this by chance. And even a fuzzer, it's trying variations on things which got coverage. You just don't get different code coverage from this until the test fails. So what do? The basic approach that we ended up taking here is that we pulled out an SMT solver. That's satisfiability modulo theories, which is an extension of the classic 3-SAT approach. So who here knows what 3-SAT is? I'm so sorry. 3-SAT is a classic computer science thing. Imagine we have a long series of logical formulas over Boolean variables. So we say A and B is equal to C, A not C is equal to D, C or E is equal to F, and the goal is to determine, is there any assignment of values to those variables that makes all of the equations true? Unfortunately, this is a hard problem. More specifically, it's an NP hard problem. In fact, it's an NP complete problem, meaning that every NP hard problem can be framed as 3-SAT. So it's basically the kind of like nastiest exponential search you can imagine. And therefore, in software testing, we're just like, yeah, let's make everything into that. Because then if we can solve that, we can solve anything. And so the goal here is that by... have to save the file again, that's a good tip. If we can solve that then, we can have our computer reason through the failure and find the exact value. And there it is. It's found a falsifying example in about 1 second of runtime. We could just make this number larger, right? We're like, well, let's add some more digits. That should be fine. We'll run this again and see how long it takes. Oh, still instant. So how does this work? Any guesses? Examine the code object. Almost, but not quite. Because in general, we might not have access to the code objects, and runtime introspection is a sin that Hypothesis is deeply guilty of, but not in this particular case. We do, for example, construct strings and then execute them in order to get nice wrappers for your code, but that's a different story. The way this works is that under the hood, Hypothesis is making a sequence of choices. Booleans, integers, floats, strings, bytes, and so on. And everything else we do is built up from those objects. And we've collaborated with the author of a library called Crosshair, which wraps Z3. And what Crosshair does is it gives you a proxy object, which will pretend to be a Python type, but by the power of doing crimes in dunder methods, it instead records every comparison or every operation that takes place on that object. And then it renders those as the series of formulae for the SAT solver called Z3. And then asks Z3, okay, here's the path that I took through the code. Is there a different set of input variables that would make me take this branch instead? And then you repeat that process until you've taken all of the branches, you've had every comparison return equal and not equal, or greater and equal and lesser, taken every branch in each direction. And once you've done this, you're kind of done testing. This technique is not actually magic. It's really, really cool when it works, but it's also relatively fragile. It works best with pure Python code, and one of the joys of Python is that it's so easy to execute code which is not in Python. It was written in C or Rust or some command line tool, and the solver will not be able to follow the logic through those. But what we found is that it's a fantastic complement to the coverage-guided testing and to the random testing, where you can use each tool to get past the barriers that the others have trouble with, all having written a single, very natural-looking test function. So that's kind of the test file, and then morally speaking, like, this is all the configuration you need. You import hypothesis settings, you tell it to use the given backend, so this is an experimental but pretty well supported interface. You register that profile, and then just based on an environment variable, you load whichever profile you like. And so you could do this based on whatever logic you want. Integrating Crosshair into the fuzzing tool, HypoFuzz, is an ongoing work in progress. So that is how we can go look for bugs and find exactly the single input that would make our test fail. And the last thing I want to talk about is, I mentioned at the start, observability. A problem that people have had with hypothesis and similar tools is that they often feel that they don't really know what it ran. And you can get every input that you tried printed to the terminal, but just, has anyone done data analysis here? Yeah? Is your favorite form of it just dumping thousands of lines of output on the terminal and then looking at it? Yes? Well, good news, you can still do that. It's allowed, I won't stop you. But for those who like graphical interfaces, we have defined an observability mode. And so the idea here is that for each test case that we run, we jump a JSON line blob which describes what test function was this, what arguments did we use, how long did it take to run in various ways, what was the output. And then we also have a couple of other APIs here that you can call. One is event. This is basically just logging something that happened, and then we aggregate each unique string that we saw in that. And so you can go, what was the distribution of sizes, for example, of some list? What fraction of the time did I take each of these possible enums as a value? And we also have target, which is like an event, except that hypothesis will also try to maximize the value of this. So you can say something like, try to maximize the contention for this resource, or try to maximize the size of this thing, or try to minimize the amount of free space. And hypothesis will actually do a structured search for that. And then we also have, there's a VS Code extension called Tyche, which is also a standalone web interface for those who prefer other editors, which can actually give you a graphical breakdown of what's happening there. The other nice thing you can do is, because this is just a JSON lines file full of stuff, you can do anything else that you can do with a JSON lines file. Anyone used pandas? Anyone used dataset? Same people. It's beautiful, and you can just explore the data in the web. Let's see if I can do a live demo of this one. We're about to find out. Okay, let's add Okay, so we've just added a little bit of metadata here. We've said, like, well, we'll track the distribution of what type our top-level object is, and also, if it's a thing that has a length, what size was it? And if I have configured everything correctly, we now have our very convenient breakdown. So we had 96 unique test cases out of a total of 115 attempts. And hypothesis will stop after 100 attempts. So some of these override, 4 duplicates. Let's have a look at the actual unique values. Compression level. We had timing breakdown, so we spent most of it generating the data, that is the byte string here. If we look at this round trip, we had more invalid examples for the JSON blob. If we look at the samples, they look pretty reasonable. So we had 3 where the thing looked like this, 3 with the empty list. And we start to see some kind of cursed Unicode. Pro tip, hypothesis users will feel more pain from Unicode than most people. I hope you feel that's a good thing. You can see the cumulative time broken down in various ways. And we can see the sizes. So this gives us kind of sense that most of the things that we saw were pretty small, but some of them got much larger. So, observability, I think it's pretty cool. And so that is Hypothesis New Superpowers. Thank you so much for sticking through with me through the slides and the live demos.